Welcome. I'm currently thinking about the Lagrange problem in finite geometries. It's a very concrete, down-to-earth problem. The setup is that we are in a finite topos, in a finite set of sets with additional structure. These face maps can be encoded in a matrix, this Dirac matrix. Additionally, we need a dimension function. This additional structure is necessary, like if we have an open set in a simplicial complex, then we cannot just from the matrix alone say what the dimension is. This is an example of a very small delta set, right? It has one element. So the Dirac matrix here is just a 1 times 1 matrix which has the 0. I have to say what Betty number this is. When I worked on graphs already, I was always looking at the Dirac matrix, and additionally also had the dimension function, which is convenient then if you want to kind of split it up into blocks and you want to compute the Betty numbers. Finite set of sets is a finite topos. It's not yet geometry because we don't have calculus, we don't have cohomology. Finite abstract simplicial complex is very simple also. It's an example where we don't actually need to prescribe the matrix D and the dimension because it's all given. Also, if you start with a graph and we produce, of course, the simplicial complex from that graph. So that's Whitney. And then we have also a topology, a very nice topology, non-Hausdorff, but the closed sets are just the subsimplicial complexes. We have here a natural topology, and we can look at open sets. I looked at the cohomology of open sets, which is very interesting. We also have level sets, and that's actually what I want to look at. When we look at calculus, you look, of course, at the Lagrange problem. So you have, when you have Lagrange, you have level surfaces, level curves, and so you have also a function which you want to extremize on this. This has been done by Lagrange in 1811. So the modern way to see this is that the gradients have to be parallel when you have a maximum. What is the discrete analog of this? And now we have a kind of a calculus because we have a framework where we can look at level surfaces, and the level surfaces are always manifolds. And so here is an example I actually took here just for illustration, not a finite graph, but I took just a part of a flat torus, or a flat plane. It doesn't matter, but it's just flat because the curvature is constant 0. It's kind of the discrete analog of what we are looking at in calculus when we look at Lagrange problem in 2 dimensions. And then you can look at the level curve. That's what I have here plotted. I don't know whether one can see that, this level curve, otherwise I will display it here. You have the level curve, which consists of all simplices where the function changes sign. And that's an open set, right? Because if you have on an edge, you have the change of sign, and it's every triangle which contains this edge. Also the function changes sign. So this is an open set, and you can then, from that, you can produce a graph, if you like, and this graph is, in this case, just always a one-dimensional manifold or empty. That's the SAR theorem. And here I drew just a function, an additional function f, and I drew a level curve of a function f. And so when you change here the function values, maybe let's just do that, you can change the function values, and then this discrete manifold changes, and then at some point you are reaching a maximum. And so I kind of tried to also kind of put the function values, visualize the function values, but you see kind of what happens there. We have no linear algebra, we have no notion of gradient. How do we deal with that? It's a very interesting question. Also, when we look at products, earlier on actually just looked at this and then look at all the connections between such sets where one is containing the other. That's the barycentric refinement. That's again a manifold. If you started with a manifold, this is a manifold. If you take the barycentric refinement, in general, if you just insist on staying in this small framework, then this is not anymore the simplicial complex. Here, kind of, if you look at this product, this is not a triangulization, right? It's not a simplicial complex. So there are kind of there are kind of cells which are not simplices. And so you can see this as a finite abstract CW complex, which is an interesting structure too. CW complexes are more complicated data structures. When you are implementing that, you have to say kind of what the cells are and how you attach it. It depends on the history, how you've attached cells. That's a much more complicated object than an element in the topos. Maybe a remark here about kind of this Dirac picture. When you have a Dirac operator, you have really calculus. You can have you have an exterior derivative, you can look at the Maxwell equations, you can look at anything you're doing in calculus, because you have Discrete curve, you have Stokes theorem. That's actually much simpler. Maybe it's just also something I was fond of when I was in grad school. That was just a time when this book came out. I had actually the French version, and the picture I love of Con, that you actually put the framework so that you can generalize things from the commutative to the non-commutative case. So if you look at measure theory, the non-commutative case is for Neumann algebras. If you look at topology, the non-commutative case is a C-star algebra. If you look at differential geometry, the non-commutative case is a spectral triple. So you can, for example, define the geodesic distance once you have this operator D. I was working in grad school on factorizations of Schrödinger operators because of isospectral deformations, and that all was motivated by trying to get the grip on the entropy problem for symplectic maps, which is actually just finding the determinant of some random operator or an element of a type 2-1 for Neumann algebra if you want to be fancy. And it's a spectral problem, and I tried with isospectral deformation to get the grip on it. By the way, here a couple of years ago I managed to get a total type equation or a Lux type equation for D, so you can deform this D. Once you have this D, you can make an isospectral deformation of this D. Similar than Witten deformation is also a deformation of the Witten deformation is a deformation of the Laplacian. This is a deformation of the Dirac operator, and it doesn't change the Laplacian, but it changes distances. Now, a very curious observation, which is maybe a week or two old only. If you have two functions on a manifold, so you have two functions on a manifold, you can think about this as a complex valued function, and then that's new this fall, I didn't have this in 2015, is that if it takes these two, if you force it to have these two values and you assume that it takes three values, then you get a manifold. But that's different than if you take the complex conjugate, you get a different manifold. And I can show maybe an example of kind of, I take a random function, complex function on a four-dimensional manifold, and I draw the surface, which is psi is equal to 0, and then the second surface, psi bar is equal to 0. So this is actually, in general, in the very small, there are different topological types in general. So that's very interesting. So of course, if you take a large enough G and the function is smooth enough, then these manifolds, like here, these manifolds will be the same. But if it's very small, right, what actually happens if it's very small here? If you take this very small, what actually happens, then it really matters. Every triangle matters. Maybe I show also there's an example of where you see the level curve of x squared minus y squared is equal to 0.1, which is one hyperbola, and then x squared minus y squared is minus, and then you have the opposite hyperbola. You can always assume, it doesn't matter if you take a function. I took here random functions. You can always take just functions taking values in plus minus 1. So both the real and imaginary part can take, both functions can take values plus 1 or minus 1. How I kind of looked at it in 2015, 8 years ago, so I had that an n-1 manifold. Also, it would have another n-1 manifold, but I could not put them together. If you take all the vertices where the functions just change sign, that's not a manifold. It contains kind of two manifolds. It's fatter. It contains two manifolds. It contains this manifold, possibly even more. Because you want to have level surfaces of complex valued functions, level surfaces of quaternion valued functions, etc. What happens here is kind of interesting. Is there some notion of gradient which allows you to kind of formulate the Lagrange problem in a way which is similar than in the continuum. So here in the continuum you want to have parallel gradients, and somehow what you definitely have to look at in the discrete is the gradient is kind of on a simplex is kind of everything which goes from the negative to the positive. So it's kind of a pair of the vertices which is where the function is positive and the vertices where the function is negative. So in this case I can visualize this. So in this case I have a function visualized on a triangle taking these three values on the triangle. Here a function g taking these three values, and I draw these gradients. They are not parallel, and indeed what happens here, this is a triangle in one of these sets. It's actually in this case in psi is equal to 0. But I just have to look at the complex conjugate. If I change g to minus g, then this will be in this. So it will not be in this. So it's kind of a little puzzle to what is the right notion of critical point, which you have in the Lagrange case, which you can express using the maximal rank condition not being satisfied. So let me stop here.